So first, let's take a step back. So suppose I want to solve this equation, the famous old quadratic equation, the bane of high school freshman or in Tennessee senior. So how do we get the formula for this, right? So what was the trick? We did something called completing the square, right? So what do we have to add to this to make it a perfect square? It was like, what, half of that squared? So it's like that. And then kind of the magic here is this was some kind of crazy thing. And if we extract the square root of that, and that's kind of an important thing. I get the square root of a squared minus 4b over 2, right? And then I bring this over, and I get x is minus a plus or minus, let's say plus or minus a squared minus 4b over 2. And of course, if this looks a little bit unfamiliar, it's because I assumed at the outset that my coefficient of the x squared term was 1, right? And of course, you can always do that because even if it's 7, I can just divide everything by 7 and that makes my life easier. Now, I take this down memory lane, and there's one more thing that I want to bring up, and that is how many solutions of that do we have? I've got 2, right? Plus or minus 1. Agree with that? Notice this comes up. Quadratic formula. Now, how about this one? Now, there's an obvious solution here, and that's x equals 1, right? But this and this one corresponds to x equals 1. This factor gives me a couple of exotic complex numbers. I'm going to call one of them omega. Using my quadratic formula, that's one solution to this. And if you take this, or if you like the I notation, minus 1 plus I radical 3 over 2, if you actually go through and multiply this out, cube it, you will get 1. And what's the other solution? Well, and this is actually the complex conjugate of the first, right? It's also the square of the first. And notice this equation here tells you quite a bit because omega and its complex conjugate are the 2 roots of this thing right here, right? So in particular, right? And this is synonymous with complex conjugate in this case. So when I take that root of unity and add it to its conjugate, I get -1, right? So I'm going to use that too. In fact, I'll kind of preserve this over here. And omega plus omega bar is equal to -1. By the way, you can see this directly over here, can't you? Because when you add omega and its complex conjugate, the complex part disappears, and I get -1, right? By the way, let me point this out because this might be useful later. Notice that one is the root of this as well. I should call this X. How many of you have ever seen this? In the complex plane, the roots of unity are spread out evenly over the circle, right? So my omega is here. My omega bar is here with the cube root of unity. But with the fifth root of unity, they should spread out a little different here. And I forget which side, maybe here. That's not a very good pentagon. I'd probably squeeze it more this way. That's the idea, right? And in fact, you can solve this by writing X. Have you all ever seen this little new plan? How many of you have seen this identity before? If you've had a really good, you've probably seen it at least by Calc 2, but if you had a good trig class, you might have seen it before. But you can use this to get this. Notice that 1 is at the angle 0 and 2 pi and 4 pi, etc. When you divide that by 5, you get 2 pi over 5, 4 pi over 5, 6 pi over 5, 8 pi over 5 back here. But I'll bring that up later. Okay, so here's my tools. My quadratic formula, I had a plus or minus, right? The interesting part of it, plus or minus. Let's attack the cubic. And the first thing I want to do is get rid of some noise. Now, cubic is more of a mess because now I've got x cubed right. I'm going to do something sort of like completing a square to make this a little bit simpler. I am going to get rid of the x squared term by doing the following change of variables. And notice, really, this is just going to shift our answers a little bit, but what's the point? Well, this is a big mess. And this step is really I'm gonna start all over this step, and I'm gonna show you if you can do this. This looks awful, doesn't it? But there's something wonderful that happens. I'm gonna cube this out. This is z cubed. And then the cube is, so the next is 3 times the square of this times this. So it's gonna be minus, no, 1/3. It depends on this, a over 3. So these should all be a's here, my bad. When I cube this, I get z cubed, I get the 3 times the square of this times this, and the 3 that I get from this term cancels this. And then I get what? I get the square of this and 3 times this, so that's going to be 3 a squared over 3z, and then that's what I got when I did the first bit out. Now, what comes out of this? Well, I get az squared. And let's see, I'm gonna get 2 times the product of 2 then times the a, so I'm gonna minus 2a squared over 3c plus a cubed over 3. And then some other crap. I don't really care anymore, right? Because what happens to the quadratic term here? The z squareds vanish, right? Everything's left as z cubed and then z1 and lower in the terms, right? The quadratic terms, the only ones vanish. So when I do the substitution, that means I can basically erase this. that makes my cubic a little bit simpler to deal with. And so I, being a very simple fellow, will deal with a cubic that looks like that. Right, because I can always do a change of variables to get rid of the quadratic version. Okay, so I made it there, but what can I get out of this? So remember how in the quadratic, you took a square root at some point and you had the plus or minus. I am going to assume a solution of this form. Actually, this will have 3 roots in the complex numbers, right? I'm going to assume a solution of this form. Okay, that's not really doing anything yet, but I'm going to show you I'm going to try to use some symmetry here. So here what I'm going to try to do is I'm going to try to do what I think is the analog of what happened in the quadratic where you have that plus or minus square root. I'm going to assume that out there in the depths of some Stephen King novel is a solution that looks like this. So that the other solutions look like this, right? This is sort of like the third root of unity analog of the plus or minus, right? Only you've got sort of 2 minuses that I change out. Now, let me point something out. And this is sort of the justification for why I might want to do this. What happens when I add my 3 roots up? You get S, so add up this column, and you get S times omega squared plus omega plus 1. Add up this column, you get T times omega plus omega bar plus 1. 0. And notice my multiplier of the square term is 0. So this should be very effective here. Let's see what comes out. So if I could make this work, then what I have is x cubed plus ax plus b should be x minus root 1, x minus root 2, x minus root 3, right? Because those are my 3 roots. I'm not going to do all the s plus t crap until I absolutely have to. Okay, if I multiply this out, hear me now and believe me later, I get x cubed, right? I get x squared times R3. I get x squared this way, R2, x squared R1. That's a good sign. Right? And that's the point. The 3 roots, I've already said, we have to set this up. The 3 roots add up to 0. Right? Then my linear term, 2 x's, right. I get, for the linear term that is, I actually 2 r's and an x, 2 r's and an x, 2 r's and an x. So I get this R1, R2, plus R1, R3, plus R2, R3, X. And finally, the constant term should just be the product of these. Right. So far, so good. Now, this is where it starts to look depressing, but remember, you must always have faith in the math, because it will take care of you. All right, let's play match game, right? This thing should be 0. Ding, ding, ding. I've already won on this. This thing should be what? A, right? So let's write these equations down. R1, R2, plus R1, R3, plus R2, R3 should be A. And R1, R2, R3 would be what? Should be negative B. Everybody agree with that? Okay. Now, at this juncture, I mean, this looks like, I mean, so far it doesn't look like it's getting better, does it? And in fact, I'm gonna make it worse because I'm gonna change all those R's into S's and T's, right? Let's see what this is. R1, R2 is, well, let's see what it is. R1, R2, let's see, that's gonna be omega S squared. And then I'm gonna have ST, right? Everybody agree? ST omega bar, ST omega. And finally, I get omega bar T squared. Everybody okay with that? That's R1, R2. R1, R3, omega ST. Wait, let's do more organized. This is omega bar S squared. This is omega ST, omega bar ST. So that's the same stuff we had before, isn't it? And finally, omega T squared. And finally, R2, R3, this last bit. Well, okay, you want to tell me. What's omega times omega bar? 1. Everybody agree? That number times its complex times 1, fantastic. So that first one is just S squared. What's omega squared? That's omega bar. What's omega bar squared? It's omega, right? So it does this kind of little dance. And finally, omega bar again is T squared. And there, I've completed this off. This whole thing should equal A. Right? But let's look closer. What happens when I add those up? S squared times 1 plus omega bar. This is the big fat 0. Same thing here. Right? And by the way, what's omega plus omega bar? -1. And there's 3 of them. So this becomes the much simpler equation. -3 ST is equal to A. Okay with that? Okay, what about the last one, right? Well, I'm almost there because recall this first one is R1, R2. So all I got to do is multiply this top thing by R3, and that'll be that. Let me just write this down. This is omega S squared, and I might as well write minus ST plus omega bar T squared times omega bar S plus omega T. And this should be minus B. I okay with that? So let's multiply this out and see what we get. Omega times omega bar, 1 again. So S squared. Well, let's see.
Cube, right?
That's cute.
Yes, cube.
I'm sorry, thank you, S cubed. That's suspicious. This is going to be omega squared S squared T. So this is going to be omega bar S squared T. This is going to be minus omega bar S squared T from this right here. And this is going to be minus omega st squared. And finally, pushing this through, omega bar times omega bar is omega, right? And so that's going to be omega st squared, and this is going to be t cubed. And let's hope that's right, and it is. Look at what happens to all the stuff that's got omegas in it. This one and this one are killed. Romeo, Juliet. And we get our second equation. Right. S cubed plus T cubed negative. Everybody okay with it? So this is fine. Second equation. Now, I want to take this one and solve for T. And I get T is equal to A over minus 3S. Right? Now, you might protest a little bit and say, well, Jim, what happens if S equals 0? What if it does, right? Go back and look at this. So I challenge you to kind of look at this. What happens if S equals 0? It kind of works out. If S is 0, we would have already had the solution. Plug this in here, right? It's S cubed minus, well, that's going to be a minus minus, so it's going to be plus A cubed over 27 S cubed. Minus, yeah, I was freaking out there. There we go. S cubed minus A cubed over 27 S cubed, that's good, is equal to negative B. Okay. And so what I am going to do is, what am I going to do? I'm going to multiply both sides of that by S cubed to get S6 minus A cubed over 27 is equal to minus B S cubed. Does that look like it works? Looks good. All right. And so, see what a genius I am, because I have taken a cubic equation and turned it into a 6th degree equation. Well, I guess I have, but what? Right. This is very special because this is actually quadratic in the variable S cubed, right? Think of this as X and that's X squared, right? I can solve this because it's quadratic. And what do I get? Well, I get S cubed is, thank goodness we have the quadratic formula, negative B plus, actually plus or minus. I'm going to just take plus root for now. The square root of B squared minus 4/27 A cubed. Actually, that would be plus. Plus 4/27 A cubed over 2. And what do you suppose T cubed is? Well, T cubed should be minus B minus S cubed, right? So basically, reverse the sign of this and then add B to it, or well, subtract B from it. And actually, no surprise here. Notice if you take s cubed and t cubed together and add them up, this quadratic square root disappears and you get negative b. Right? So in other words, when I first wrote the s cubed down, I said, let's just forget about the negative for a while, but this takes care of it, right? The other solution is picked up there. So this gives us our solution. It gives us one of the roots. My root one of the roots for this that's plus b. So it's the cube root of the first thing plus the cube root of the second. Negative b plus square root of b squared plus 427 a cubed over 2 plus the cube root of negative b minus the square root of b squared plus 427 a cubed over 2. That's one way to write one of the solutions. Now, I'm going to go further with this in a minute, but first of all, dear audience, this is one reason why you don't see this in high school. Right? It's a bit of a hot mess, isn't it? And the other roots involve putting the complex cube root of unity, omega here, omega bar here, and then reverse the roles for the third root. And of course, this brings up an interesting question. What happens when all the roots are real, for example? So let's look at a couple of examples of this. I'm going to start off with this one here. Let's just try our solution here. Now that we're armed with this wonderful formula for one of the roots. Let's read the following. This is kind of a good warm-up test case for this. Now, in the real world, please don't use this formula, right? Not on this one anyway, right? Does anybody see one? One is root of this, right? Yeah. That looks right. So one is a root. What are the other two roots? Gross. Yeah, they're gross, right? The other roots are, so one comes out of this one, and one minus 28 over 2, right? Which is minus 1/2 plus or minus 3/2 by 3i, right? Those are the other two. Let's see what this thing does for us, right? And this was kind of a warm up. This is a good test case because here, if we use the formula, let's see, I guess my roles of A and B are agreed. So let's see what our formula gives us. I get right. B is -7, so it should be 7 plus the square root of B squared, which is 49. And then A is divisible by 3, which makes this convenient. So when I cube this, the cube cancels out that. So this is 4 times 8, which is 32. over 2 cube root of 7 minus. What do you want? Right? That's what the point tells us. What is 49 plus 32 is 81. So the square root of this is 3. So this is the cube root. Not the fourth root. The square root is 9. So it's 16 halves is 8. And this is 7 minus 9. Divided by this. So this is cube root minus 1. So I get, oh, what did I do wrong? Oh, I didn't do anything wrong. This is 2 minus 1. And there we go. Fantastic, right? But kind of the cool thing about this is if you multiply 2 times omega minus 1 times omega bar, it should turn out to be that. Right? You should probably check it. And when you reverse it, it should give you the other one. Now, let's do another one. Similar to this. This one, it almost looks like I'm ripping it off. And the reason it looks that way is because I'm like ripping it off. So notice again, just like the previous one, this has a root of 1. So this is now I emphasize this, I don't care about the other roots in this case, but would everybody agree that 1 is a root and the other 2 roots are complex, that are not real, right? So the other 2 are complex conjugate, right? So that trailer quadratic polynomial has no real roots. So when you put this in the formula, here we have A is 3, B negative 4. Then what do I get now? Well, I get R1 is the cube root of negative B is 4 plus the square root of B squared, which is 16, and then 4/27 of A cubed, so that's going to be 4 over 2 so far. And the other piece should just the same thing with a minus on the square root. Right? Now recall that 20, well, square root of 20 is 2 radical 5, right? So this is 4 plus 2 radical 5, so this is cube root. 4 over 2 is 2, 2 radical 5 over 2 is radical 5. C minus 5. Now, would everybody agree that that number, that crazy crap number I've got up on the board, is a real number, right? Because the things under the square root sign are positive, and under a cube root sign, I don't care anymore, right? Because it doesn't matter if it's positive or negative. How many roots of this were real? Only 1. And that one real root was 1. There is no alternative for that to be 1. Check it. That's probably the strangest way you've ever seen one written. It's cube root of 2 plus radical 5 plus the cube root of 2 minus radical 5. Everybody okay with that? Good. Yes. All right. Here's one that I really designed to make you angry. Let's look at this one. Now, I'm gonna do what I did before I get into the fancy schmancy stuff over here. I wanna figure it out. Does this one have an obvious root?
Keep going.
If you notice, the structure of this polynomial, although similar, is slightly different than the others, right? And we're gonna see that's gonna have an effect here in just a moment. Okay, so if I factor out one is the root of this, right? So this has got a factor of x minus one to it. So this is x cubed, no, it's not, x squared, plus x minus 20, I guess. Agree? What about this? This actually factors quite nicely, as a matter of fact. So this has three real roots. Namely 1, 4, and -5. Agree? Let's try forming. Now something a little different happens for this one. And I think you'll see it pretty quickly. For this animal here, my A is -21 and my B is 20. Right? So cube root. Okay, so my B is, so that's gonna be -20 plus the square root of 20 squared. And then yucky, I've got to cube that and multiply by 427. Fortunately, this is 3 times 7. So the 3 cubed cancels the 27. So this, it turns out to be like 7 cubed times 4, which is going to be like 1372, I guess. Over.
Sure.
Minus 20 minus cube root of 400 minus 1372 over. But, uh-oh. So what's under the square root is negative 972, which is 81 times 12. Yeah, is minus 8 times 4 times 3. So the square root of minus 972 is going to be 18 radical -3. So this root turns out to be the cube root of -10 plus 9 radical -3 plus the cube root of -10 minus 9 radical -3. Notice that this is a complex number that's not real. Or is it? Each separate piece is a complex number that's not real. When you add them up, turns out to be real. Now, which one? Which one of those 3 roots is that one? Anybody want to take a guess? Well, it depends really on how you define the angles and such, but I think if you take the principal values here, let's see if we can figure out which one it is. If you take the cube root, so if you take the cube root of a complex number. How many of you have seen this, where you write a complex number is, it's like polar coordinates, how far it is away times its angle. The cube root of this, it shrinks it, takes the cube root of how far away it is, and what does it do to the angle? Takes about a third. Right? So let's look at these numbers here. -10 plus 9 radical -3. So I'm going to call this the IY axis. This is the imaginary axis. So this is in the neighborhood of 50, a little bit bigger, right? That many units up. And so forget the cube root for a moment. 10, 1.5. So this would be about -10 plus 9 radical 3i would be right here. And the other one under the cube root is the conjure of that, right? So it would be down here, sort of symmetric. I drew that a little better. Right. So what happens? What happens when I take the cube root of this to this number? You're going to be, I'm almost like an engineer up here. I'm just kind of estimating, right? But it's going to be a third of the angle. Everybody agree with that? And a cube root of the distance. And same with this, it's symmetric, right? Third of the angle, cube root of the distance. So this is my primitive rendition of the cube root of, good Lord, that's burning the retinas out of my eyes. This is not the greatest color. This is the cube root of 10, I'm sorry, -10 plus 9 radical -3. And this is cube root of -10 minus 9 radical -3. Can anybody eliminate one of the roots now? Because the actual answer, because of my beautiful drawing, you all can see that what happens when you add this up, what happens to the complex part when you add these two vectors up, if you will.
It blows up.
It disappears, and it basically, it's the sum of the x coordinates is where you end up. So you want to guess that? What's the root that it can't be, if my picture is right? It can't be -5. Everybody agree with that? How do we figure out what it is? Well, we need to find this angle here, right? And what is this angle? Let's see, I think it's here. How do I get this angle? Well, it's 1/3 of whatever this original angle is. Do I agree with that? And how do I get the original angle? Well, basically, I have this triangle here, length 10 and length 9 radical 3, right? That's the size of the triangle, right? And so actually, the angle should be inverse tangent 9 radical 3 over 10. But we're in the wrong quadrant, so I'm going to take minus that. Right? And what did I do to get down to the red one? I took a third of that. Right? So that's the angle. So if I want to find the x coordinate of that, because remember, when you add this vector and this vector up, it should be just twice this x coordinate, right? The y coordinates cancel out twice that. How do I get the x coordinate? Well, I need to know this length here, right? I'm gonna need a cosine, I'm gonna need to know the length here. What is the length? Well, it's the cube root of the length of this. And the length of this was what? It's like 100 plus 81 times 3, right? So it's like 343. So the length of this is the cube root, the square root of 343. But lucky me, 343 is actually a perfect cube. So this turns out to be square root of 7. Right? So this x coordinate here should be cosine of this angle that I've got by taking a third of this angle, and then multiply it by radical 7, and then multiply it by 2, because you add up 2 of these things. And the answer is 4. So that is probably one of the weirdest pseudo trig identities you've ever seen. The 2 radical 7 becomes a cosine of 1/3 quantity pi minus inverse tangent 9 radical 3 over 10 is 4. Check it. It's true. Yeah. Okay. So with this, actually, let me point out that you can use variants like this. Notice that plus Rx minus R plus 1 you can do variants of this by figuring out polynomials that have root 2, root 3, whatever you like. And I did another variant with the minus 21x and 20. So you can do like x cubed minus Rx plus R minus 1, something like that, equals 0, also has x as a root. And play games with this and come up with all kinds of crazy things that will make you the most popular person on campus. So, any questions? Questions? All right. Anybody have any questions? Yes.
So how do people came up with the first assumption of, let us assume that the roots are s plus t, omega s plus omega conjugate t.
I'm not saying that I invented that because I probably didn't, but I thought of that sort of on the trying to use the symmetry, because if you do that, it'll make the 2 columns add up to 0, which is exactly what you get when you listen to quadratic term. So it's just something that, it was just something to try. That's what, a lot of the old mathematicians before they had computers and stuff to do, they would do these kind of clever little tricks, right?
Yeah.
That's one of the most, I mean, I know that people in differential equations would probably get mad at this, but one of the things I always like the differential equations for all the kind of really neat, clever tricks that people came up with, so. Okay, other questions? All right, well, stay tuned for next week. Should be a lot of fun. I hope you guys don't get killed in the snowstorm next week. So, everybody enjoy it. Yeah, there's supposed to be more snow. So, but anyway, you all have a good weekend and we will see you next week, I hope.